Okay, so we're not learning anything brand new for the derivative purposes. We're just kind of applying what we know and what we know how to calculate to different scenarios. So that, again, the type that there's a lot of reading and pausing to wrap your head around what you're even being asked to do is the most challenging part. Once you wrap your head around what you're being asked to do, you will find that these aren't that hard, but that's the big challenge, is figuring out what the heck you're supposed to be doing. So in this first one, we're given a line. This line, we want it to be tangent to this graph, okay? And so essentially, what will B need to be in order for it to be a tangent line to this graph? So first of all, this is a format of a line that doesn't do much for us. We usually get more out of y equals mx plus b. So I would rearrange this to y equals mx plus b. And if you visualize adding y to both sides and subtracting b over, that'll be 6x minus b. Is that an easier question regarding this problem?
Can I have another that?
Yes, you may. So now what do you know about this tangent line? What feature about this tangent line can you now put your finger on? Slope is 6, okay? So if the slope of the tangent line is 6, we want to figure out where it is that the slope of our function is 6. Do we follow? Okay, so we're going to try to find where the derivative of our function is equal to 6. In order to do that, we need to find the derivative of our function. Okay? Now, we have two different techniques at this point for kind of finding the derivative. If we're looking for the derivative rule, do we use the traditional limit as h approaches 0, or do we use the alternative as x approaches a value? If we're looking for the function rule. The traditional derivative method is what gives us our rule. Remember that the alternative method that we learned yesterday gives us really the slope at a specific point and a specific point only. And we're not looking for the derivative at 6. We're looking for when the derivative will equal 6. So at what point will it equal 6? So we're going to look for the derivative rule, and that is going to come from the limit as h approaches 0. F of x plus h minus f of x all over h, and then a whole bunch of cleanup. So I'm going to square my binomial. Distribute my negative. Keep distributing. Combine like terms. And then divide by h, because now I can. All the terms have an h in it. So it's going to be my limit of 6x plus 3h. And that is, when h approaches 0, that's just going to be 6x. Okay? So f prime of x equals 6x. We were looking for where our slope was going to equal 6. So when does this equal 6? At what x value? 1. Okay? So that's not b's value, but let's, again, wrap our head around what's going on here. If I graph 3x squared minus 4 for you, what we just found, I got to change my window, is that at 1, So at this location on the parabola at 1, we have a slope of 6. Okay? So we have a tangent line there at 1 that we're essentially trying to find the equation for. Yes? Okay? And we have part of it. We know that the slope of it is 6, but how are we going to find B? How do you find B? We just found X. What'd you say? Plug in that point. What point? 1 comma... It's not...
not 1, 6.
Where's the point on the parabola? 1 comma something. I don't know what it is, but you can plug in 1 and see what the point of tangency is.
Yeah.
Right? So if you go over to the function and you find f of 1, you're going to get -1. So the point is 1, -1. That point is on your parabola, but that point is also on your tangent line. So if you know that that point is on your tangent line, you're going to bring it over to your tangent line, plug it in, and find B. So we have -1 equals 6 times 1 minus B. Subtract your 6 from both sides. -7 equals -B, so 7 equals B. And you're done. Okay, if you want that visual confirmation, we can graph 6x minus 7, and you'll see that it's a tangent line. Okay? If I change my window from -5 to 5, it'll be that much more clear that at 1 we have a tangent line now. Okay? Any questions on that? All right. So again, what I said was, you have all the skills. It's just kind of synthesizing everything, putting it together, figuring out what you need to calculate using, you know, there, again, not any method of steps that I can give you. I just have to tell you, you got to think it through. Next example says, for what value of x in the interval from -1 to 3 does the instantaneous rate of change of this function equal the average rate of change of the function? Okay, so again, for a visual, I'll show you a picture of the function we're looking at. And we're only interested in a certain interval, yes? The interval from -1 to 3. So when I graph this, I'm going to graph it and only do it on the interval from -1 to 3. So here's the function from -1 to 3. They want to know for what value of x in this range does the instantaneous rate of change, so is that's the instantaneous rate of change is the slope of the curve at any given point. When does that equal the average rate of change? So you can see the average rate of change from start to finish. You can see that it's negative anyway, right? So if that line, my pencil right now, is representing the average rate of change, we're looking for the moment in time that our instantaneous rate of change, in other words, our derivative, in other words, the slope of our tangent line, any way you want to look at it, is also this same slope value. So if I just kind of keep my pencil and like at that angle and just slide it, it looks like it's tangent right about there. Agree with that? Okay, so this would be the instantaneous point. We got to find out what x value that's going to be. At what instant is the instantaneous slope of the curve the same as the average rate of change of the curve from start to finish in this interval? Do we follow? So what would you first calculate? Average rate of change. I agree. So before we can do that, we need to come up with the y coordinates for those 2 points. So when we plug in -1, we get 1 plus 4, which is 5. When we plug in 3, we get 9 minus 12, -3. So our average rate of change is 5 minus negative 3 over negative 1 minus 3, which is 8 over negative 4, negative 2. So, what are we going to do with that? Great. We know the average rate of change is negative 2.
Are we going to solve for the derivative and then find it in that x value when it equals negative 2?
Correct. If we know our average rate of change is negative 2, we need to set our instantaneous rate of change equal to negative 2 as well. And your instantaneous rate of change is the derivative. That's what the derivative formula gives you. So we need f prime of x to equal negative 2 and find out at what x value does that occur. So, again, we need to find the derivative equation and find out when it will equal negative 2. So this is a traditional derivative formula. We should be using that h approaches 0. F of x plus h minus f of x you're distributing all of your combining, and then dividing by h. So your simplifying is done. Evaluate the limit now. You get 2x minus 4 is your derivative. And like I said, we want to know where is that going to equal negative 2. Add 4 to both sides. 2x equals 2. X equals 1. So for what value of x? 1. And I think on our graph, that would have been your guess based on the visual, right? Again, there was the average rate of change. If I slide it down until that becomes a tangent line, I think that was a pretty good estimate. Right? Right there is the point of tangency, which is at an x value of 1. Okay? I mean, we wouldn't be able to tell with the naked eye if that was 1.2, though, so you have to do it algebraically just to make sure. Okay, and also, this graph is just to help us conceptualize everything. We're obviously not going to have a calculator at our disposal. Okay? All right. Next. We're given a table of values for f of x. We're asked to use the table to approximate what f prime of 1 is going to be. What is the slope of this function at 1? Thoughts? If you have a bunch of points, let's pretend for a minute that we have a bunch of points. Here, they give us that point, that point, that point, that point, and that point. And this is at 1. How would you find, given just these points, well, you're given all 5 points, how would you find the slope to the best of your ability, because it's not going to be perfect, but how would you best approximate what the slope is going to be at that point? Sonny?
I think the average rate of change of that point and the point go off the right closest.
Okay, so take the average rate of change from here to here if you think that's closer, or from here to here if you think that's closer. Well, if you look at your point, the one to the left is 0.02 units away, and the one to the right is 0.02 units away. So they're actually both the same distance away, so,
And maybe between the up and the right point, not the middle.
okay, so maybe this rate of change,
Yeah.
a little bit to the left, a little bit to the right, and obviously that's the slope of the secant line if you find the slope between those 2 points. But if you do slide that down, it is pretty close to the slope of the tangent line. So I think that's a good idea. I actually think there's 2 approaches to that. That would be one of them. Just the point to the left and the point to the right, find the average rate. Obviously, the closer you get surrounding your point of interest, the better off, the more accurate your secant line slope is going to be. So that would be one option. My other thought actually piggybacks off of your first gut instinct, which was find the slope between these 2 points, but I would also find the slope between that point and the one after it and maybe average them together. Does that make sense? Yeah, so the slope before would be a little bit too little, and the slope after would be a little bit too much, but then average those slopes together and it would put you as close, right in the middle, but hopefully as close to your tangent slope as possible. Does that make sense? Okay. So we'll actually do this one both ways. On the left-hand side, I'm going to do the slope between the 2 surrounding points. So my slope is going to be 0.725 minus 0.689 over 1.02 minus 0.98. Which is going to give me 0.36036. Nope, I don't remember. Hold on, I got to use my calculator. 0.036. Oh, I did remember. Oh, well. Divided by 0.04, which is 0.9. And that's probably not exact, but it's a good estimate. Okay? And then the other thought was to find the slope twice. Once between these 2 points, and then a second time between these 2 points, and then take your 2 slopes and average them together. So your slope going into the point of interest, your slope coming out of the point of interest, and then the average of the 2 of them. So for the one up here, it would be I'm just going to cheat, 0.707 minus 0.689 gives you 0.018. Oh, the devil. 0.018 divided by 0.02, which is 0.9. And the slope after the fact actually also ends up being 0.018 divided by 0.02 equals 0.9. And averaging those 2 would give you 0.9. So either way you do it in this case, it's the same. They probably would be slightly off, and I don't think one is going to always be better than the other. I think depending on the scenario, depending on the points that you're given surrounding a point, sometimes this way would be better, and sometimes this way would be better. They're going to be virtually the same, though. I don't think you're going to find much difference between 2 techniques. I don't like this example on this function because it's not a linear function, but the first 4 points are linear. If you look at the difference from here to here and here to here and here to here, it's all the same. It's slightly different here. So when they give you a linear function, that's no fun because you could have just found the slope between any 2 points and you would have had it, which is not the intention. I don't know why the book provided that example, but I pretended like it wasn't linear, and I gave you a parabola to look at. But does that make sense? Okay. All right. One more. All right, we have a function that contains the point -2, 1. I'm always going to recommend a sketch. I have no idea what that function looks like other than the fact that it goes through -2, 1. And then they're going to tell me one more piece of information, that the slope of my function at that point is 5. So I can maybe, 1, 2, 3, 4, I can maybe draw an approximate tangent line to my function. But again, there's a gazillion functions I can draw that would go through that point and have that line as a tangent line. We just need to come up with one just to kind of wrap our head around what's happening here. So to keep it simple, I'm just going to do a parabola. Okay, so they're saying if this tangent line is going to be used to approximate the value of the zero of the function, then what would that be? So the idea here is that because this point is so close to the x-axis, that the tangent line at that moment will have an x-intercept or a root that's very close to the actual root of the function, and you can see that here. The x-intercept of the tangent line is very close to the x-intercept of the actual function. So even though we don't know what the actual function is, we're going to use our tangent line because we actually can come up with the x-intercept of the tangent line. And they're not the same thing, but this is going to be a good approximation of the actual root of our function. Do we follow? Okay. So how would we go about proceeding to find the x-intercept of the tangent line? Don't be shy, Emma. Well, I know that. I didn't mean that's why you were shivering. Come on. What am I going to do now? To find, essentially, how am I going to find the x-intercept of this tangent line? Noah.
Since we know that at that point, the slope will be 5, we can use that. So it would be like -3, -4 would be our other point. So your next one.
-3. Oh, so you went down 5 and over left 1?
Yeah.
So you're finding a second point to do what with it?
To get the...
You're not wrong. There is a second point down here.
Mhm.
And you can come up with it exactly. So why did you do that? What are you going to do now that you have a second point?
The intermediate value theory?
I like it, but no. Brian Beck. Sorry, Sonny. You're next.
Since you know what the slope is, couldn't you plug it into the slope formula and solve for, like, what the value is you're looking for?
Tell me what to write. I don't follow.
5 equals, and then that point is -2, 1. You could do, x minus 1, and then 0 minus -2.
I think I know what you're saying, and it can work. I think you're trying to do the slope formula between this point and that point.
Yeah.
But this point, think about it. This is x, we don't know the x, comma 0. Isn't the y-coordinate of any x-intercept 0?
Yeah.
So it would be y2 minus y1, which would be 1 minus 0, over x2 minus x1, which would be -2 minus x. Yes?
Yeah.
So it will work. That is, I've not thought of that once today, but it is logically sound and it will work. We will multiply, cross multiply, you get -10 minus 5x equals 1. Add 10 to both sides. You're going to get negative 5x equals 11. Divide both sides by negative 5. X equals negative 2.2. Sonny, what were you going to say? Because this was definitely the lesser obvious of the options, I think.
Well, at negative 2, 1, the slope is 5, you have a point, you have a slope, you can plug that into the formula.
Right, just write the equation of your tangent line. You have a point, negative 2, 1. You have a slope of 5. So just write the equation of your tangent line using point-slope formula. And then once you have the line, like any function, you can find the x-intercept by setting, how do you find an x-intercept? You set y to 0. So we would just plug in a 0, and you're going to get negative 11 over 5 again this way. I just think this way is more true to kind of what we've been doing. Go ahead and just write the equation of your tangent line, because you can, and then try to figure out why that was helpful, what you were doing with that. Good. Either way works. Any questions? Okay. So tonight your homework is multiple choice. I'll project it up here in a minute so you can start it. It's on my webpage for what you don't finish here, but also we already did 2, 8, 18, and 20. Those were our class examples. Those are the 4 we just went over. So there's no need to redo those. Just on a separate sheet of paper, do everything else. Okay?